Welcome to an example of free undamped motion, which we now know we can describe using these linear second-order homogeneous differential equations. These equations are equivalent, just in different forms. So we're told an 8-pound weight attached to a spring exhibits simple harmonic motion. So we know the weight W equals 8 pounds. We want to determine the equation of motion if the spring constant is 1 pound per foot and if the weight is released 6 inches below the equilibrium position with a downward velocity of 3/2 feet per second. So next we know that the spring constant is 1 pound per foot, which is K. Next, the weight is released 6 inches below the equilibrium position. So looking at our diagram here, that means this length here, x, the displacement, will be positive 6 because it's below the equilibrium position. If it was above, it would be negative. And this occurs at time t equals 0. So we know x of 0 equals 6 inches. But since the spring constant is in pounds per foot, we need to convert this to feet. 6 inches is 1/2 a foot. We're also told it's released with a downward velocity of 3/2 feet per second. And again, because the velocity is downward, the velocity is positive. If it was upward, the velocity would be negative. So at time t equals 0, the velocity is positive 3/2 feet per second. So x prime of 0 is equal to 3/2 feet per second. Now notice, to set this up, we have to find the mass. Since we have the weight, we can use the formula mass equals weight divided by g, the acceleration due to gravity. So in this case, the mass m would be equal to 8 pounds divided by 32 feet per second squared, or just 32. So this is simplified to 1/4. The units here would be 1/4 of a slug. So now we can take this information, set up the differential equation, and then using these initial conditions, we can find the equation of motion. Let's go ahead and use this form here. So we'll have x double prime plus k divided by m, which would be 1 divided by 1/4, times x equals 0. Well, 1 divided by 1/4 is the same as 1 times 4/1, or just 1 times 4. So we have x double prime plus 4x equals 0. Now from here, we should recognize that this is a linear second-order homogeneous differential equation with constant coefficients, and therefore we can solve this differential equation using a characteristic equation. So for a quick review, because our differential equation fits this form here, we're going to set up the characteristic equation, and then based upon the types of solutions, this will tell us the form of the general solution. And in our case, we're going to have complex roots, so our solution will fit this form here. Let's go ahead and show that work. Notice how here a equals 1, b equals 0 since there's no x prime term, and c equals 4. Which means the characteristic equation would be r squared plus 4 equals 0. So if we subtract 4 on both sides, we would have r squared equals -4. And now taking the square root of both sides of the equation, notice how we have r equals plus or minus 2i. Which if we wanted to, we could also write as 0 plus or minus 2i, because if we go back and take a look at our notes, if the solution is complex, we want it to be in the form of alpha plus or minus beta I. So here, if alpha is 0, notice how we have e to the 0 here and e to the 0 here, which is 1, leaving us with c sub 1 cosine 2t instead of x, plus c sub 2 sine 2t. So this would be the general solution. And now we'll find the equation of motion by using these initial conditions. But before we do that, I do want to point out one thing. Notice how in this form, if we replace k divided by m with omega squared and set up the characteristic equation, it would look like this, giving us r equals 0 plus or minus omega I, and therefore if we perform the substitutions for alpha and beta in this form that we use to find our solution, we could simplify it to just x of t equals c sub 1 cosine omega t plus c sub 2 sine omega t. So you may see this in some textbooks, but I normally prefer to show the work with the characteristic equation. And since we know that x of 0 equals 1/2, that means x of t is 1/2 when t is 0. So notice if t is 0, this would be cosine 0, which is 1. So we'd have c sub 1. And then here, if t is 0, this is sine 0, which is 0. So this just leaves us with c sub 1 equals 1/2. So now we know that x of t must equal 1/2 cosine 2t plus c sub 2 sine 2t. And we also know that x prime of 0 is equal to 3/2, which means we'll now have to find the first derivative. So x prime of t would be equal to, here we'd have 1/2 times the derivative of cosine 2t, which would be 1/2 times negative sine 2t times 2 plus the derivative of the second term, which would be c sub 2 times cosine 2t times 2, or 2 c sub 2 cosine 2t. I'm not going to simplify this because notice how if x prime of 0 equals 3/2, then x prime of t would be 3/2 when t is 0. T is 0, this would be sine 0, which would be 0, making this product 0, leaving us with just plus 2 times c sub 2 times cosine 0, which is 1. So this is equal to 2 c sub 2. So if we multiply both sides of the equation by 1/2, we can see we would have 3/4 equals c sub 2, which means the equation of motion is x of t equals 1/2 cosine 2t. Since c sub 2 is 3/4, we have plus 3/4 sine 2t. Let's finish by looking at the graph of our equation of motion. And here it is. I hope you found this helpful.